Astrophysics isn't just one thing. It's not just galaxies swirling in the void or equations scribbled across chalkboards. It's a field as vast and varied as the universe itself, branching into stellar evolution, black hole dynamics, cosmology, and planetary science. Even the search for distant worlds, exoplanets, rests on astrophysical shoulders. I got the pleasure of speaking with someone who stands at the intersection, Professor Sara Seager of MIT. Professor Seager is a renowned astrophysicist and planetary scientist at MIT, known for her groundbreaking work on exoplanets and the search for life beyond Earth. Her work doesn't just ask what's out there, it challenges us to reimagine what's possible.
My definition of astrophysics is astronomy as explained by physics. So if we want to understand the stars, galaxies, our solar system, really anything, it's how do we use known equations of physics to understand what's around us. Well, my favorite project right now relates to our planet Venus, which you can often see so bright in the sky. Like it's often the brightest object out there in the night sky. Well, we are studying and building instruments for a series of missions to go to Venus, public-private partnership missions that are small and focused and are going into the Venus atmosphere directly, specifically to probe the cloud particles to search for any interesting gases or solid molecules that might suggest the presence of life, like very primitive life in the Venus atmosphere.
Venus offers us a close-up view of the atmospheric chemistry, dense clouds, acid rains, greenhouse effects we can probe with direct measurements. But TESS, the Transiting Exoplanet Survey Satellite, works from a much greater distance. It doesn't study the planets we know, it searches for the ones we've never seen. Led by MIT and launched by NASA, TESS scans the entire sky for subtle dips in starlight, tiny eclipses caused by planets passing in front of their stars. With its 4 wide-field cameras, TESS covers 400 times more sky than Kepler, examining over 500,000 stars nearby. Its mission isn't to find Earth 2.0, not yet, but it can find rocky worlds orbiting small, cool M-dwarf stars. These stars, more common than our Sun, make the search more practical and more hopeful. If Venus teaches us how planetary atmospheres work, TESS helps us find the planets whose atmospheres we haven't studied yet. It's the start of a cosmic shortlist for future missions hunting signs of life. So between Venus and TESS, it sounds like you have a fascination with looking for exoplanets.
Right, exoplanets and the search for signs of life beyond Earth.
Now, when you say search for signs of life beyond Earth, you're not hoping for any kind of Star Trek first contact sort of thing, just looking for the little microbes and molecular life, right?
Right. I mean, we're trying to do whatever we can. So I just try to remind people to be patient. I know everyone wants to meet the little green humanoid, but
that would
right
be wonderful.
Now, it would be great. We're just looking for signs of life, gases that don't belong in an exoplanet atmosphere. Like here on Earth, we have oxygen, which is so reactive. It really shouldn't be present in our atmosphere. It is because it's continually produced by life. So I'm not sure what level of detail you want to get in here, but if we can find a gas that is indicative of life, we literally won't know if it's intelligent beings or if it's just output by the simplest life form you could imagine.
You can go into as little or as much detail as you want. I'm giving you free rein here.
I see. Okay. Well, I will give you some detail. Right now, we have in the news, it's in April 2025, and then for the last couple months, it's now June 2025. There's been a gas detected. There has been a report of a sign of life on an exoplanet, and that exoplanet is K218b. It's not like Earth, it's actually much bigger. It's the kind of like person who drops her keys under drops her keys, but she looks under the searchlight because that's where you can see. So K2-18b is bigger than Earth. It's easier to study than an Earth. We can't study an Earth twin yet. And astronomers have reported the detection of a gas called DMS, dimethyl sulfide. On Earth, it's made by phytoplankton in our ocean. But when it comes to exoplanets, we have to ask ourselves, when it comes to the signs of life, we have to ask ourselves 3 questions. The first question, is the signal real? I'm sure you've had that before where you've taken an image of something and it's a bit blurry or smudgy. You're like, I'm not sure if that's real or an instrumental artifact. So we have data and it's quite noisy. We're really at the limit of what we can do, what the James Webb Space Telescope can study. So there's a lot of arguments in the community about if this particular signal is real or if it's just noise. So that's number 1. Let's assume the signal is real. We can move to number 2. Is the signal attributed to the right gas? Is it indeed dimethyl sulfide, or is it another gas that is not associated with life? Those 2 things we're working on. We can get better data. We can try to get more of a handle on what molecules could be out there. So we're working on the first 2. They're astronomy and chemistry. But let's assume now that now or later we have a signal that everyone believes. We have assigned that signal to the appropriate gas we all agree with. Now we're on number 3. Is that gas produced by life, or is it produced by some other chemistry in this very, very exotic exoplanet? And that number 3 is where we're all kind of stuck right now, because we can't spatially resolve the exoplanets. We don't really know much about them. And so we're getting a bit stuck now. We thought it was really simple before. Just find a gas like oxygen. It's so reactive. It shouldn't be there in context with the environment. And now what? So it's kind of exciting, right? To be at the time when we can fight about this kind of thing. But it's also a bit frustrating. Well, it was the mid-1990s, and I was a graduate student looking for a thesis project. And I was actually at Harvard University, which, because they're well-funded and they have a very great spirit of exploration, my thesis advisor suggested perhaps I want to work on exoplanets, which were literally just discovered months earlier. So most places you wouldn't work on something like that because it's so new. Nobody thought it was real. People didn't think exoplanets were real. They thought it was binary stars, because in those days the detections were made with radial velocity. The wobble method, like the star is not stationary because the planet is orbiting it. The star and planet are actually orbiting their common center of mass. You can say the planet's gravity causes the star to wobble. And we astronomers, I think some amateur astronomers can do this too. You're measuring what's essentially the line of sight motion from the Doppler shift. So you're measuring the line of sight motion of the star. But is that because the planet is orbiting the star? Is the star wobbling because another star is orbiting the star? Or is the star pulsating and it's also moving towards and away from you? So people were arguing about what was this, because everyone was expecting a solar system copy, a Jupiter far from the star, not what was discovered, the first exoplanet around a sun-like star, 51 Peg b, that is many times closer to its star than Mercury is to our sun. So the whole community didn't think it was real. They thought the signal was real, but that it was misattributed to a planet. So my advisor suggested I work on these, in particular study their atmospheres with computer models. And I said yes. So sometimes it's luck, there's a lot of, luck. Luck is one word, but I don't know how you would describe it. Like, there is luck that comes your way, but you have to take it. The best way to get involved, if you wanted just my opinion, like on how to get started as an amateur, it's to join a club or attend some club events. I grew up in Toronto, Canada, and I'd like to give a shout out to the Royal Astronomical Society of Canada and the Toronto Centre. I'm so proud to be the honorary president of the entire RASC right now. I've been visiting all the chapters. I got my start there as a child because my dad took me to a star party where the amateur astronomers have their telescopes outside and welcome the public. That's one way to get started. And last summer, I went back to my home province, Ontario, And there is an annual event called Starfest. And did you know there's like 1,000 people out camping for a weekend? Actually, it's several days, actually. Unfortunately, our weather was not good. It didn't rain, but people come with their telescopes, and there's all kinds of people. There's the people in the camper vans with the super fancy equipment. There's people sleeping in their car just there with friends. Like there's people who don't have a car. They get a ride with a friend and they like see the night sky for the first time. It's like a ginormous field and dark sky. So there's ways to get involved where you're just literally visual eye or joining the club, or not even joining, but participating in some events. I think that's the best way to get started. So for professional, it's a different story, harder. But the goal is to learn math, physics, computers. It's not to learn astronomy right away because you really have to build the fundamentals. And being able to do math and physics is really important. And programming now. Pretty much every branch of astronomy requires some level of programming. You don't have to be a professional computer programmer, but understanding code, knowing how to manipulate code. Today, we all do use ChatGPT to be like a partner. It's not going to get the job done for you. You can do some work. You have to check it and make sure it's right. But learning how to program is really important as well. So I'd say all of those things. And then what's important is to go to a university where there's at least some research going on. It doesn't necessarily have to be astronomy research, but being able to get a flavor either through a course for credit or if you're lucky, a summer job in some kind of research, because research is completely different from homework problems, like getting assigned a math problem or computer problem or even an astronomy problem. So getting some experience with research, either through a class project or a summer job, hopefully, is really the way to go. And those are the ways to get started there.
If you're looking for a place to start with coding, the Hour of Code is a global initiative designed to make computer science accessible to everyone, especially kids. Through fun, one-hour coding activities, it demystifies programming and shows that anyone can learn the basics. Supported by educators in over 180 countries, Hour of Code has reached tens of millions of students worldwide. Professor Seager recommends it not just as a scientist, but as a parent. She's seen firsthand how engaging and empowering it could be for young learners. In her community, it was a regular part of encouraging curiosity and digital literacy, and she even participated with her own kids. Astrophysics may begin with equations and telescopes, but it thrives on human curiosity. From the clouds of Venus to the flicker of alien worlds discovered by TESS, the pursuit of knowledge stretches across light years and lifetimes. Professor Seager's journey reminds us that discovery isn't limited to distant stars. It's also found in classrooms, in coding experiments, and in the spark of a question asked at the right moment. Whether you're charting your own path in science or simply stargazing with wonder, the cosmos offers space for everyone willing to look up and ask what's possible. Thanks for watching. If you like this video, smash that like button. Click that subscribe button for more content from Texas Dark Skies, and ding that notification bell to get notifications when new videos are posted. Take care of yourselves, and in the words of my favorite personal astrophysicist, keep looking up.